Welcome to a new video in a series on numerical linear algebra, and this video is about the householder reflector and the QR factorization. So we've previously introduced one way of finding the QR factorization of a matrix, and we've talked about its importance in the theory. So let us recall what the decomposition is. So we aim at writing any matrix A as a product of two matrices, one of which is unitary and the other is upper triangular. So we've seen that one way of achieving this goal is by what's so-called Gram-Schmidt procedure, where what we do is that we take the columns of A and we transform these by this process to an orthonormal set of vectors. Now these vectors will form the matrix Q, that is the desired unitary matrix we're looking for, and R can be gotten by just using this form and multiplying both sides by the inverse of Q, which is in this case the conjugate of Q, and we get the matrix R, which is an upper triangular matrix. Now another way of finding this QR factorization of a matrix uses the householder reflector as a tool. So for that, let me give the idea of the method, and then I'm gonna define what the householder reflector is. So here's the goal. Okay, so before we started with a set of vectors, which are the columns of A, and we transformed them to the orthonormal set. Now what we're gonna do is that we're gonna start with the matrix A, and we want to transform it to an upper triangular matrix. So the end goal is to reach an upper triangular matrix. Okay, let's see how we can do that. So one way of doing that is to take each column and zero out the entries below the diagonal entry. So we start by zeroing out these entries. Okay, and we hope to find some matrix Q1 that is unitary, such that when we multiply it by A, we zero out the entries below the diagonal entry, and we get a new matrix of this form. Okay, so now that we've zeroed out the entries below this, we want to zero out the entries below the second diagonal entry, which is this. So we want to zero out these ones. So again, we hope to find a matrix Q2 that is unitary, such that when we multiply it by the last matrix we had, we zero out the entries below this diagonal entry, and so on and so forth. We keep multiplying by unitary matrices so that we get an upper triangular matrix, which we're gonna call the matrix R. So let us see what would happen if we did this. So if we could find these matrices, if we could find these n-1 matrices, which when we multiply A by, we get an upper triangular matrix, this whole thing will be a unitary matrix, which we're gonna call Q star, or Q inverse in this case, because Q is unitary. And have we done that, we will be done, because we would have found the QR factorization of A, which is just in this case QR, where Q is just this thing after we take the inverse of it. So it's gonna be Q1 star, Q2 star, Qn-1 star. Okay, so if I tell you now how to find these QIs, these intermediate unitary matrices, you will have a new way of finding the QR factorization of a matrix. So for that, let us see how to do this. Okay, so let us see what kind of matrix we're looking for. Okay, so here's the kind of matrix we're looking for. We're looking for a unitary matrix H such that if we hit it by a vector, say a vector of this form, we get a vector of the form a new entry, a new first entry, and then zeros below that. Now, before we investigate what h is, let us try to find what this entry would be. So if we call this entry A and we call the vector x, we notice that the 2 norm of hx would be just the square root of a squared plus 0 squared plus dot dot 0, because the 2 norm of the left hand side is equal to the 2 norm of the right hand side, and we'll be left with this vector, and this is just the absolute value of a. Now if you recall, one property of unitary matrices is that if you take the 2 norm of hx, it's going to be just the 2 norm of x. Okay, so what we're saying is that we want a unitary matrix such that when we apply x to it, we get the 2 norm of x times e1, the vector e1, where e1 is just 1 0 0 0, right? Okay, and now that we've understood what we require from h to satisfy, which is this equality, we're gonna try to understand the construction of h geometrically, and then we're gonna give the explicit formulation of h, which we're gonna call the householder reflector. Okay, so let us see how to do that. Okay, so if we start with a vector x, the vector, the norm of x times e1 will be somewhere here, right? Somewhere on the x-axis. And this, we require this to be h times x, because this is what we're expecting from h, right? This is the expectation that we've shown here. Okay, and here there's a simple trick that we want to recall, which is that what is the projection of a vector x onto a vector v? This is simply v star over v star v times x. Okay, so this is actually the definition of the projection of x onto another vector. So what you do is that you take the outer product of the vector you're projecting on with itself, and then you take the norm of that vector. You notice that this is just the norm of v squared, right? Because it's just the inner product of v with itself. And then you multiply this matrix, because this is an outer product. This is actually a matrix. You multiply this matrix with the vector x, and doing so, you would project x onto the vector v. Okay? So we're gonna do a trick. We're gonna pick a specific v, which is this vector. This vector is gonna be this vector over here, after we add to it this vector, and the resultant will be this vector. So this is the vector v that we have. So let me clean this up and then redraw v. So this is the vector v that we have. Okay. So keeping in mind that this is the projection of x onto v, let us see what happens if we project x into v. Well, this is a simple geometric fact. You will notice that if you project x onto v, that you will get this vector, right? This is the projection of x onto v. So long story short, this is all to say that the vector v is in fact equal to minus 2 times the projection of x onto v, because if you take this vector, you scale it by 2 and you take the opposite direction of it, you will get the vector v. Okay, so now that we've seen this, we're ready to define the householder reflector. Why? Because remember, what is v? V is this thing over here, right? Let me just put an equality here. So this is v, right? So this is the vector v. And now if we just rearrange terms, if we bring this to the right hand side, we get that x minus 2 times the projection of x onto v is equal to the norm of x e1. Okay, and this is just another way of writing the identity minus 2 times the projection onto v times x. And look at what we've just found. We've just found a matrix here, which is a matrix which we're gonna call H, right? Such that when we multiply by x, what we get is this thing. And this is what we were looking for. Remember, this is what we're looking for, right? This is the thing that we're looking for. So here's the definition. Now that we've motivated the definition, here's the definition of a householder reflector. A householder reflector, it's defined as the identity minus 2 times a projection matrix onto some vector, right? So, and the idea of the algorithm we're about to define is that given a vector x, right? Given a vector x, and say you want to zero out the entries below the first entry of x. So, and to do that, you introduce a matrix H of v, which is the householder reflector for a suitable choice of v, and you hit it with x, and you get the vector, the norm of x times e1. Now, what is the suitable choice of v that we want to make? Well, this is one choice of v that is possible to make, right? It is this choice of v that we've took, which resulted in the following. If you multiply x by the matrix identity minus 2 times projection onto v, you get this vector. So you make this choice over here, and you multiply x by that vector. So now that I've told you how to zero out the entries below a vector, let's go back to the goal. So now you know the matrix that you want to multiply this matrix by to zero out the entries below this vector, to zero out these entries, right? However, there is one little thing that we need to account for. When we multiply this by q1, that is okay, that is perfect. We can take this to be h of some v, right? And that is perfect. However, we want to account for something over here. Over here in the second column, we don't want to zero out the entries from the second entry on. What we want to do is we want to keep this entry, and we want to zero out the entries below that. So we want to zero out these entries. So one way of doing that is, instead of applying the matrix H of v, the new H of v, instead of applying it to the whole vector, what we're gonna do is that we're gonna apply it just to this vector. So how do we do that, right? So to do that, we're gonna introduce a 1 here and zeros elsewhere, and then we're gonna use the matrix H of v that would help us to zero out the entries below this entry. And if we do that, we will be preserving this entry. We won't be zeroing it out, and we will instead be zeroing out the entries, the 2 entries over here. Okay. However, again, if we continue the process, when we reach the third column, the only thing we want to zero out is this entry, right? Because we want to zero out the entries below the diagonal. So to zero out the entries, just this entry, what we want to do is that we want to apply h of v to just this vector, right? We don't want to apply it to the whole thing. So how do we do that? What we're going to do is that we're going to define q2 to be the matrix, the new matrix we want to multiply by. We want to define it to be the identity 2 right? It's as if that we're taking 1 0 0 0 0 1 0 0, right? We take an identity here, this is identity 2, and we filled out these with zeros, and in this block we use h of v. In this way we'll be restricting the action of h of v to this place, right, to this block of matrix. In this case we'll be zeroing out just this entry as desired. And excuse me, I should have called this q2 and this one q3. Okay, and now to wrap up, let me just summarize what I said. Okay, so what we're gonna do is that we're gonna define qk to be a block, which is just an identity that is k minus 1 by k minus 1, and we're gonna take the householder reflector of the corresponding vector that we wanna zero out the entry below it, and we define these qk's for k equals 1 to n minus 1, in fact. Why do we do that? Because we can stop at n minus 1, because the number of columns we want to zero out the entries below are these things, because this is the thing we want to zero out, right? So these are the things we want to zero out. So we can stop at n minus 1, right? And so we define n minus 1 unitary matrices, and when we multiply these by A, we get an upper triangular matrix, and this over here will be the definition of our Q inverse, because when we multiply by Q both sides, we get that A is equal to what? QR.